As large language models scale to hundreds of billions of parameters, full parameter fine-tuning becomes a massive hardware bottleneck. To update a 70 billion parameter model, standard backpropagation must store not only the frozen model weights, but also gradients and optimizer states for every single parameter. For standard AtomW optimizer, this results in a staggering memory overhead of 16 bytes per parameter on top of the model weights. Full parameter fine-tuning of a 70 billion parameter model thus requires a minimum of several hundred gigabytes of high-bandwidth memory, mandating expensive multi-node GPU clusters. This physical resource barrier shuts out most research labs and developers. How can we perform high-quality model adaptation without updating billions of parameters? The key to overcoming this parameter barrier lies in a profound theoretical insight: the hypothesis of low intrinsic dimension. Empirical work by Agajanian and colleagues demonstrated that during fine-tuning, the parameter updates, delta W, do not require the full high-dimensional space of the original weight matrices. Instead, the learned weight updates actually reside in a subspace with a much lower intrinsic dimension than the original weight matrix. This means that although a weight matrix may project representations across thousands of dimensions, the actual structural updates needed to adapt the model to a new task can be captured with incredibly low-rank representations. Low-Rank Adaptation, or LoRA, exploits this intrinsic property by freezing the original weight matrix, W0, and representing the weight update, delta W, as the product of two low-rank matrices, B and A. For a weight matrix of size D by K, we introduce trainable matrices B of size D by R and A of size R by K, where the rank R is chosen to be much smaller than D or K. The overall weight update is scaled by alpha divided by R, where alpha is a constant hyperparameter. Crucially, matrix A is initialized from a Gaussian distribution, while matrix B is initialized to 0. This ensures that delta W is exactly 0 at the start of training, maintaining the model's baseline behavior perfectly at step 0. While LoRA reduces trainable parameters, QLoRA, or quantized low-rank adaptation, introduces three critical innovations to shrink memory footprints even further. First, it uses normal float for an information-theoretically optimal quantile quantization scheme for normally distributed model weights. Second, it employs double quantization, which quantizes the quantization constants themselves, saving an additional 0.37 bits per parameter. Finally, QLoRA uses paged optimizers, which leverage host-to-device memory paging to gracefully manage temporary memory spikes during backward passes. Together, these synergies allow a 70 billion parameter model to be fine-tuned on a single consumer GPU without any performance loss. By decoupling model adaptation from full parameter updates, LoRA and QLoRA have transformed the landscape of modern deep learning. They reduce trainable parameters by up to 99%, cut GPU memory requirements by more than threefold, and maintain mathematical equivalence during inference by merging the low-rank adapters directly back into the base weights. This co-design of hardware-aware quantization and low-rank approximation forms the modern foundation of parameter-efficient fine-tuning. To keep exploring the elegant mathematics and hardware mechanics driving modern AI, subscribe to Gemini 3.5 Flash Model. Let's keep optimizing the future of computation.